Hey chemistry peeps, Jess McCartney here. Let's look at some space blankets. I'm sure everyone has seen pictures of these blankets. They're used in hospitals and all over the place, and they don't look like they would be very warm. They're not made of like nice fluffy material like our blankets that we use on our bed, but they're actually designed for a specific purpose. So if you remember back from last lesson that our bodies go through what's known as respiration, and we naturally produce thermal energy. Well, these blankets are used to capture that thermal energy that's naturally being produced. So 90% of the radiated body heat that's being produced is collected by these space blankets or trapped by these space blankets. So they're designed to keep us warm by the heat that we're already producing. In today's lesson, we're going to be looking at enthalpy changes and combustion reactions. So looking at the study design dot points. We're going to be comparing exothermic and endothermic reactions in reference to bond making and bond breaking. So we did touch on exothermic and endothermic last lesson, so we're going to be looking at that in more detail and what that means in terms of for the reaction to proceed or not. We're going to be looking at enthalpy changes, and you'll see this sign a lot, and this is noting the enthalpy change, and this is measured in kilojoules. And then we're going to be looking at the molar enthalpy changes, and that's measured in kilojoules per mole. So we're looking at both of those. So take note on when we're looking at the unit change. Then we're going to be looking at enthalpy changes for mixtures. So therefore, this will be in kilojoules per gram. And we will be looking at representations such as energy profile diagrams. And last of all but not least, we're going to be looking at limiting reactants in a chemical reaction. So let's get started. So according to the law of conservation, energy cannot be created or destroyed. So this means that energy can only change forms. So we are moving it from one place to another. So when a change occurs, it's possible for the energy to be lost or gained to the surrounding environment. So because of this, we can actually put labels on that, and that's what we're going to look at today. So a chemical equation is sometimes being described as a system, and this description will occur more as you go through Year 12 chemistry. So the equation being a system. Often energy is released or absorbed depending on the reaction that is happening. Now, this release or absorption of energy can be in the form of heat. So you can actually feel it getting hot or cold. This heat can also be described as thermal energy. Heat energy can be converted into other types of energy, and this is important for scientists. So how can we utilize this energy that can sometimes be waste to something that's useful? So it can be used as light, electricity, or kinetic, depending on how it's captured. Chemical reactions can be classified based on the thermal energy that's released into or absorbed from the surrounding environment. So whether the substance or the reaction is getting hot or cold. Now, you've probably already heard the term exothermic reaction before. But what does this mean? So let's have a little bit of refresher for this. So when we're thinking about an exothermic reaction, it's the total chemical energy of the products is less than the total energy of the reactants. So we may have heard exothermic reaction being talked about hot and cold and all that type of stuff, which is correct. It can be measured by the thermal energy, but we as Year 12 students need to start thinking about the actual energy in the products and the reactants. That's how we're going to describe that. The energy will be released from the system into the surroundings. So if the energy is released, that means that the outside is going to feel hot. The released energy can be shown as exiting the system. So sometimes you may see it in a chemical reaction as a product. So as energy being a product. And this is how you may have seen lots of reactions written in Year 10 and 11 chemistry. The most naturally occurring exothermic reaction is respiration, which we spoke about in the last lesson, and combustion. So like in an exothermic reaction, we need to start thinking about endothermic reactions as the chemical energy in the products and the reactants. So an endothermic reaction is the total chemical energy of the products is greater than the total energy of the reactants. And I am going to show you some diagrams very, very soon that will show that in better detail. So because of this, the energy is actually absorbed from the surrounding environment. So you'll actually feel it go cool. So that's with an endothermic reaction. Endothermic reaction takes place in a container, and so like stated, it will feel cold to touch. So you will actually feel that decrease of thermal energy. The absorbed energy can be shown as a reactant. So when you're writing energy, it will be on the left side. So it's classified as a reactant because it's being absorbed by the system. Decomposition reactions will sometimes show an endothermic reaction. It's not always consistent, so it's not as easy as an exothermic reaction. We state combustion and respiration. We do know, however, that photosynthesis is also a very well-known endothermic reaction. So in chemistry, we can represent energy in multiple different ways. So we can look at it as just writing energy on the equation, or we can actually use it in terms of the energy change and use what's known as this delta H symbol. So when you see this delta H symbol, this is looking at the energy change from the reactants to the products. So thermochemical equations will include the delta H value for the chemical reaction. Now, generally, it's measured in kilojoules, but sometimes it might be measured in a unit that is different. So just make sure you're keeping an eye on that, just so that you are using your calculations in the right units. So like I stated before, delta H is the symbol for change in enthalpy, okay? So enthalpy change is a measure of the amount of energy absorbed or released during the chemical reaction. So whether the energy is being released to the environment or absorbed from the environment. Delta H is determined by subtracting the enthalpy of the reactants from the enthalpy of the products. So how much energy you have in the reactants from how much energy you have in the products. So this is a nice little thing to have in your notes, showing that calculation there. This measurement is given relative per mole of the substance. So therefore, if your ratios change, your enthalpy will also change, and we will have a look at that in a little bit. And this is also easily converted to mass volume if needed by using those mole formulas. And again, we will have a look at that. So like stated before, I said I would show you some diagrams. So these diagrams, I think, make it a little bit easier to understand that energy absorption and release. So when we're looking at an exothermic reaction, energy is released to the surrounding environment. So this means that the products, the enthalpy of the products, will be less than the enthalpy of the reactants. So you can see the products are here and the reactants are here. So the products of an exothermic reaction will always be lower than the enthalpy of the reactants. So therefore, the energy has to be released. And that's why you feel this hot occurring in those reactions. With an endothermic reaction, the enthalpy of the products is greater than the enthalpy of the reactants. So therefore, it is absorbed from the surrounding environment. So you can see here, the reactants are lower than the products. So to get up to here, we have to absorb energy. And that's why you feel this cold occurring with an exothermic reaction. Another thing to note, because of the energy difference, that an exothermic reaction is always negative and an endothermic reaction is always positive. And you will see this on some of the equations that we look at in a minute. So what is activation energy? Activation energy is the energy that must be absorbed to break the bonds in the reactants so that the chemical reaction can proceed. So you need to have enough energy supplied to the system to be able to break those bonds and for the reaction to proceed. Now, this activation energy is different for all different types of reactions. Sometimes the activation energy is very, very small, and sometimes it's very, very large. So depending on what is reacting with what. Noted that both endo and exothermic reactions have activation energy. They both have it. All reactions do. It just depends on how much energy is required. So here's some neat little diagrams for us to look at again, and these are so important in chemistry, so we're going to look at these a lot. And they look different between an exothermic and an endothermic reaction. So let's look at an exothermic one first. So remember that an exothermic reaction, the products will have a lower enthalpy than the reactants, and this will have a negative delta H, so as stated before. So you can see the products are lower and the reactants are here. Now, what this little hump here in green, this one here, this is the activation energy. This is the energy required to break the bonds in the reactants and then for this reaction to proceed. So up here is where that enough energy is supplied, those bonds are broken in the reactants, and the reaction will then proceed to the products. Now, because the reactants are higher than the products, it releases energy, so that heat. If we're looking at an endothermic reaction, the products will have a higher enthalpy than the reactants, and this will have a positive enthalpy change. So we're looking at it here, reactants are here, products are here. Now, you can see the activation energy still exists in an endothermic reaction, but you can see it's much bigger than the exothermic reaction. So much bigger activation energy, so therefore it requires more energy for it to proceed. And this is why it would absorb all the energy from the surrounding environment for that reaction to proceed. So all this energy is required, and once that happens, the bonds break and the products are formed. Now, because it requires so much energy, that energy is absorbed and that coolness will be felt. So as I said before, we're going to look at these thermochemical equations in more detail. So remember, the delta H of a reaction is looking at that energy, that change of energy from the reactants to the products. So if we have a thermochemical equation, it will always give you that delta H value. So the amount of energy in kilojoules signified by the delta H value corresponds to the mole amounts specified in the coefficients equation. So what does that mean? That means that the numbers that are in front of the reactants and the products correspond to the delta H. So you can see that there's nothing in front of this glucose here. So that means that that's 1 mole of glucose in this combustion of glucose reaction will produce 2,803 kilojoules. So that's important to think about as we're going to continue these notes. Another thing to think about is the states that the reactants and products are in, because as something changes state, it actually can release or absorb energy. So it's important to take a look at how the states are changing between the reactants and products. So when we're looking at these, for example, we're looking at the boiling water to melting ice. So it actually requires more energy to boil water than it does to melt ice. And you can see that. So even though it's just water changing from solid to liquid and liquid to gas, you would think there wouldn't be much change in energy consumption, but there actually is. So when we're looking at melting of ice, it only requires 6 kilojoules. But when we're looking at boiling water, it's 40.7 kilojoules. So quite a big difference, even though it's just changing one state to the other. So like I stated before, the mole of the equation is directly proportional to the enthalpy change of the reaction. So therefore, if you have a different number of mole from the initial equation, then therefore the enthalpy change will actually change as well. So if we are looking at this example, if we're doubling the coefficients of the chemical equation, this will actually also cause the delta H to double, as you have twice as many reactants undergoing the equation, so therefore producing twice as much energy or absorbing twice as much energy. So it depends on what the type of reaction is. So if we're looking at combustion of methanol, the equation is the same. It would just depend on how much methanol you start with in the first place. So the first one is looking at 1 mole, so nothing in front of the methanol, that's 1 mole. 1 mole of methanol produces 726 kilojoules. Now, if you have then 2 mole, you are doubling. So therefore, it has to double the amount of energy that's being produced. So you would double this value here to get the new delta H value. And that will give you negative 1,452 kilojoules. Now, obviously, if you triple it, then the value will then triple from the original again, and so on and so forth. Also note that if you are halving, then you can also halve. So these questions can be infinite in terms of what you have to do. So same as if you are reversing an equation. So if we are flipping the reactants and products around, so like if we're looking at photosynthesis and respiration, for example, if we are changing the equation around, then therefore the delta H sign also has to change. So if it is initially exothermic and we flip the reactants and products around, it will change to endothermic and vice versa. So let's have a look at an example. We have methane reacts exothermically with oxygen, so it's a combustion reaction, and we all know combustion reactions are exothermic. So methane as a reactant produces 890 kilojoules per mole. Now, if we were to flip this equation and make carbon dioxide and water now the reactants and methane as the product, it now changes it to an endothermic reaction. So therefore the sign on the enthalpy changes. However, because it's the exact same equation with the exact same ratios, the enthalpy number itself does not change. Only the sign. It's only changing from exothermic to endothermic. Generally, when we're thinking about calculations in chemistry, you have one reactant that's in excess and one reactant that's in limiting. Now, 9 times out of the 10, you are told which is which, but sometimes you are given more information that's required, and you actually have to work out which one is the limiting and which one is the excess. Now, what does that mean? It means that which reactant is going to be used up completely. That is known as the limiting reactant. Now, this is important to know because we need to use the limiting reactant to do any stoichiometry calculations after that particular reaction. So if we need to find out the mole or the mass of a product, we would need to know what the limiting reactant is first. Now, the steps involved for calculating the limiting reactant are, so the first thing we need to do is we need to calculate the number of mole of each reactant. So you will get given information for both the reactants. So you will calculate the mole of both of them. You will then determine which reactant is in excess and therefore which is in limiting. And how you do that is you work out using the ratios of the equation. So you use the amount of the limiting reactant to work out the amount of product form. So that's using your stoichiometry if the question is asking you to do that. So let's have a look at a question on a limiting and excess reactant. So a gaseous mixture of 25 grams of hydrogen gas and 100 grams of oxygen gas are mixed and ignited. So you can already see you've been given 2 lots of information. So this is a very quick indication that you have to calculate the limiting and excess reactant before you do anything else. Water is produced and collected and weighed. What is the expected mass of water produced? So the equation is given to you, which makes it nice and easy. So which reactant is the limiting reactant? Okay, so how you work through this is just following the steps that I provided in the previous slide. So the first thing you need to do is you need to calculate the mole of both the reactants. So we're going to calculate the mole of hydrogen. So using the information in the question, you have 25 grams of hydrogen. So we're going to use the mass over molar mass formula. The mass is 25 grams and the molar mass is 2. Remember, that's found on the periodic table as the atomic masses added up. 25 divided by 2 gives you 12.5. Then we're going to calculate the mole of oxygen. Same formula is being used. we have 100 grams of oxygen stated in the question. So it's 100 divided by 32. So the 32 is found from the periodic table again. It's 16 times 2 for 2 oxygens. And that gives you 3.13. Now, the next thing is looking at the equation. So the equation is so important. This one is given to us, which makes it nice and easy. But if you do have to write an equation yourself in other types of questions, please make sure you are balancing it. It's so important that it's balanced correctly. So if you're looking at the equation, you can see that 2 mole react with 1 mole of oxygen. So if there's nothing in front, we assume it's a 1. So to react oxygen, you require 2 mole of oxygen of the H2. So we need 2 lots of these to react to the 2H2 in the equation. So 2 times 3.13 is 6.26. Now you can see that the 6.26 is still less, so still less than the 12.5 calculated of H2 in the original step. So therefore, oxygen is the limiting and H2 is in excess. So the oxygen will be completely consumed, where the H2, there will be excess left over in this reaction. So if we're looking at the marking guide for this particular question, it is worth 2 marks. So the first mark is calculating the mole of each reaction. So that's this step here. So the mole of each of these gives you 1 mark. And then using the equation to calculate the limiting reactant. So that is the second mark. So in summary, the amount of energy in kilojoules signified by the delta H corresponds to the mole amounts. So however many mole you have in your reactants will then produce that particular energy change. And that will change as those coefficients change. Remember that in an exothermic reaction, energy is released and the energy of the reactants is higher than the energy of the products. And then you'll feel heat occur in an exothermic reaction, and it will always have a negative delta H. In an endothermic reaction, the energy is absorbed for the reaction to take place. The reactants have a lower energy than the products, and you'll feel that cold. And in an endothermic reaction, it will have a positive delta H. When you're calculating the limiting reactants, you need to follow the following steps. So calculate the number of moles of each reactant, determine the reactant that's in excess and limiting using the coefficients in the equation, and then use the limiting only to calculate the products. And remember, to calculate the enthalpy change, we use the H of the products minus the H of the reactants. Coming up next is the Area Study 1 Progress Check 1. I will see you then. Bye-bye.